This is the last video in a chapter on atoms, molecules, and ions. We have just talked all about moles and how we can use them to count large numbers of very tiny atoms. And now we're going to do some calculations with that. Okay, so in our discussion, when we were measuring pennies, we said the best way to measure pennies was to weigh the pennies, to convert that to dozens by weighing 1 dozen, and then to convert that into number of things, number of pennies. So in chemistry, when we are using atoms, we can measure the mass of a large number of atoms, a scoop, and then we can convert that to the number of moles, because that's our dozen of chemistry. And then we can convert that to number of things, where the number of things could be atoms, it could be molecules, sort of individual units, chemical units. So this is our problem-solving strategy, and we can go in either direction. We can go from mass to number of things, or we can go from number of things to mass. The arrows are double-sided. And so we need a conversion factor for each of these. So to convert from mass to moles, we're going to use our molar mass that we just learned about, which has units of grams per mole and can be found in the periodic table. And to convert from moles to things, we are going to use Avogadro's number, which has a unit of 1 over mole, or more exactly, things per mole. But to avoid indicating what that thing is, we just write it as 1 over moles. So let's do a couple of example problems to look at how to use this strategy to solve problems. So first, you have 2.5 grams of aluminum, probably about this much aluminum foil wrapped into a ball. Sounds about right. So in that mass, how many moles of aluminum is this? And how many atoms of aluminum is this? So if you think you can solve this one on your own, go ahead and pause the video here, and then you can play it when you're ready to see the answer. So we always start with what we know, 2.5 grams. And because we're talking about a specific element this time, we need to include the element in the unit. So that's something new we're going to start doing after this. So the unit now includes the molecular formula. Specify what compound we are actually talking about. Because some of these conversion factors, specifically molar mass, depend on what compound we're talking about. So 2.5 grams of aluminum, and then we are trying to find how many moles. So we're going to use the molar mass as our conversion factor. Remember, we can either use it as grams per mole, or we can flip it upside down, moles over gram. It doesn't matter what the orientation is. So we're going to put grams of aluminum on the bottom so that it will cancel with what we have. And we're going to put moles of aluminum on the top so that it gives us what we want. So we know it's going to be 1 mole of aluminum per so many grams. And we can find that number of grams from the periodic table. So let's have a look. Here's our periodic table. Here's aluminum. Let's zoom in as close as we can. Let's see if we can figure out what that number says. It's almost unreadable. Okay, you have to take my word for it then. That number says 26.982. Any periodic table will tell you the same. So 26.982 grams of aluminum in 1 mole of aluminum. We can multiply through. Grams of aluminum cancels with grams of aluminum. You can use our calculator to do 2.5 over 26.982. And we should get 0.093 moles of aluminum. So there's our first answer. Put that in a box. Okay, so we have moles, and part B wants to know how many atoms. So how many atoms that's a count of the number of things. So we can either start from the 2.5 grams again and convert to moles, and then to things, or if we're feeling good about the math we just did, We've already gone halfway through that process, so we can just start here for moles and use Avogadro's number to convert to number of things. So I'm feeling pretty good about this. So I'm going to go with it. Either way is totally fine, totally up to you. So we'll start with our 0.093 moles of aluminum. Remembering to carry all the digits in the calculator from that calculation. So we are going to use Avogadro's number to convert with a unit of things per mole. So the moles of aluminum goes on the bottom, and the number of things or atoms of aluminum goes on the top. It is going to be number of things in 1 mole, and Avogadro's number is 6.022 times 10 to the 23rd. And never leave space for that, it's okay. Moles of aluminum cancels with moles of aluminum, and we take 0.093 times 6.022 times 10 to the 23rd on our calculator, and we should get 5.6 times 10 to the 22nd atoms of aluminum. When we decrease the number of sig figs here, you'll see to 2 sig figs because aluminum only had 2.5 significant figures. All right, not too bad, not too bad. Feeling pretty good about our ability to work with particular elements and find how many moles and atoms there are. So let's move on to the pro level, something that you'll need to use in a couple of chapters. Let's move on from an elemental compound to a molecular compound, something with more than one type of element in it. So we're going to use glucose, common biological molecule. We have 70.2 grams of glucose with a formula of C6H12O6. And we want to find how many molecules this is and how many carbon atoms specifically there are in that mass. So let's see if we can solve this one in a similar way to the one that we used before, even though it's a little bit more difficult. So let's revisit our strategy. So we have the mass, and we are trying to find number of molecules, which is the number of things. So we need to go mass to moles using the molar mass, and moles to things using Avogadro's number. So we'll start with what we have, 70.2 grams, and we're going to include the formula, C6H12O6. Our next conversion factor is going to be the molar mass, and molar mass is in grams per mole, so grams of C6H12O6 on the bottom, moles of C6H12O6 on the top. And we know this is going to be 1 mole per so many grams. And I don't know what that is, so let's come back to that. Let's get the rest of it set up first. All right, so we put grams on the bottom there so that grams of glucose would cancel with grams of glucose. Now we have moles, and so we need to use Avogadro's number next to convert from moles to molecules. So we'll put moles of glucose on the bottom, and we'll put molecules of glucose on the top. Be careful not to abbreviate molecules as MOL, or you might think you meant moles of molecules, which is very, very different. Okay, and Avogadro's number is 1 mole of something is 6.022 times 10 to the 23rd things, in this case, molecules. And moles of glucose will cancel with moles of glucose, and we will end up with molecules of glucose. So that part is set, but we still have this blank that we left here for the molar mass. And I left it blank because unlike aluminum, which you can find listed in the periodic table, there is no listing for glucose on the periodic table because this is made up of 3 different elements, carbon, hydrogen, and oxygen. So to find the molar mass of a compound with multiple elements, we have to do a weighted average, just like we did when we talked about isotopes. So when we did isotopes, we took the mass of an isotope and we multiplied it by its abundance. So when we do this one, we're going to take the mass of each element, the molar mass of each element, and multiply it by the number of atoms in the molecule, kind of like its abundance. So we'll start with carbon. Here's carbon in the table. Here it is a little bit closer. 12.0107. That's our molar mass of carbon in grams per mole. And then we multiply by the abundance, which is 6 atoms of carbon. And then we do it for the next element. So the next element is hydrogen. Hydrogen is way over here on the left side. Here we are, 1.00794. That is the molar mass in grams per mole of hydrogen. And then we multiply by the abundance, which is 12. So that was, let's see, carbon. That was hydrogen. And now we're going to do oxygen. So oxygen is right here. And that is 15.9994. Can almost read that. Again, use your own periodic table. 15.9994 grams per mole is the molar mass of oxygen times the abundance. There's 6 atoms of oxygen in every molecule. And we will multiply that through using our calculator, and we should get 180.156 grams per mole for our full glucose molecule, C6H12O6. All right, so we did this little side quest to find the molar mass of this molecule, and now we can put it back into our calculation. 180.156 grams of glucose in 1 mole of glucose. If you'd prefer to do this first, definitely go ahead and do that. I usually prefer to get my calculations set up, leave the hole in it, and then go and fill the hole by finding the molar mass. But this is math. You can do math in any order, and you should end up with the same thing. So if we take 70.2, divide by 180.156, and multiply by Avogadro's number, we should end up with 2.35 times 10 to the 23rd molecules of glucose. Awesome. A little bit more difficult than when we had an elemental compound that only had one type of element in it, but not so unreasonable. We just had to do a side quest and find that weighted average along the way. Okay, last step. We found how many molecules of glucose there are, and then we want to know how many individual carbon atoms are there. Because remember, there's more than one carbon atom inside every molecule of glucose. So this isn't something that we covered in our strategy. So I guess we could add it if we want, but it looks like we can figure it out without a formal strategy. So if I look at this molecule, as I did when I was doing the weighted average, I noted there were 6 atoms of carbon in every 1 molecule of glucose. And so that is the conversion factor I need to complete this last step. So we'll start with what we found in the last part. So 2.35 times 10 to the 23rd molecules of glucose. And then we need to convert from molecules of glucose to atoms of carbon. So 1 molecule of glucose goes on the bottom. And so we're going to convert from molecules of glucose to atoms of carbon. Okay, and so how many atoms of carbon in 1 molecule? It says right here with the subscript in the formula, every molecule of glucose has 6 atoms of carbon. So molecules of glucose cancels with molecules of glucose. We can take 2.35 times 10 to the 23rd times 6. And that should give a bigger number, 1.41 times 10 to the 24th atoms of carbon. And this is something that's actually pretty useful that we're going to need to do towards the end of this course, when we need to figure out how many individual atoms of each element we have in a particular amount. And we want to make sure we do a bullshit test. Every molecule should have at least one, if not more, atoms of a particular element. So the number of atoms of some element should be greater or equal to the number of molecules. And we can see 10 to the 24th compared to the 10 to the 23rd, it is a little bit larger. So doing the molar mass calculation with a multi-element compound is a little bit more work, but I know we are all totally up to the challenge. If you can find a weighted average, you can find the molar mass of a compound. And that is the end of everything we need to know about atoms, molecules, and ions.